Good morning, everyone. It's our lecture number, I forgot which number, about the quantum transport in topology. And last time we started to discuss what linear sigma model is. So today I just continue the linear sigma model, and it's a very technically involved topic, so we will derive this sigma model, and hopefully by the end of this lecture we will finish the derivation. So nonlinear sigma model is the field theory that describes electrons in disordered metals, and the starting point was the rotation function z. That was just a simple Gaussian integral for fields phi and phi star. And the exponent of the action minus s of phi. And the action was simply a Gaussian quadratic expression minus I phi dagger, and then here we have what we usually have in the Green function, so the operator that we have to invert, epsilon minus the Hamiltonian, which has a created part and random potential part, plus omega over 2 lambda and plus I 0 lambda times phi. And the important thing that I introduced on the last lecture is the replica trick. So we have in total n identical replicas of our disordered system, of n replicas. And the field phi has inside two n components. One component for retarded, one for advanced, and also this pair is repeated for every replica, so it's two n components. And this matrix lambda here inside is a 2 by 2 matrix, which is just 1, 0, 0, minus 1. It's 1 for all retarded fields and minus 1 for all advanced fields. So what we have here is just a diagonal matrix. It has only diagonal elements. For retarded fields, it has plus I0, for advanced it has minus I0, and these two parts also have different energy. One is energy epsilon plus omega 2, the other one is epsilon minus omega 2. That's why I also have lambda here. And one other important thing that I forgot to tell you last time is that this phi field is actually a Grassmann field. It's a Grassmann field. I will not go into much details. Grassmann means it's a fermionic field, so these phi's anti-commute to each other. They behave almost like fermionic operators, but actually they are numbers, they are not operators. And these numbers that anti-commute, they are called Grassmann numbers. So with all this thing here, we also discussed that we can find an average Green function, well, first just the Green function, between points R1 and R2 in real space, is represented as the Gaussian integral, similar to Z, similar to this one, phi to phi star, with two additional fields here in the pre-exponential, so it's phi of R1 and phi star R2. And then there is an exponent of the same action minus S. And there should be also some prefactor here in front, and actually this prefactor is minus I divided by Z to power N number of replicas. And for the fields phi, we here take either retarded or advanced component, depending on whether we want to compute retarded or advanced Green function, and also take this field just from the replica number 1. So we have many components, we take just one component, say from the replica number 1, and on other replicas, they do not have this phi here, so they will actually cancel the denominator.
So just to make sure, so we consider phi as Grassmann variables just because they have the same anticommutator relation as fermionic operators?
Not because it was just an explanation of what they are. Actually, it's just more convenient. It will be more convenient later if we use here Grassmann variables.
Okay. So
Just Grassmann integrals will be the determinant.
no, I understand, but
yeah, that's true.
yes.
Just the determinant of this object here.
Yes, of course, but I mean like how we write actually the action. So we, yes, but we write it, as far as I understand, I write down my Hamiltonian, second quantization, and then I make transformation and write the action.
No. This is one particle Hamiltonian, there is no second quantization here.
Aha, okay.
This whole methodology applies to non-interacting systems, so you can write a single particle Hamiltonian, which is just an operator, and you want to invert it to find the Green function, you just invert an operator.
Okay.
And we put this operator between two phis just to define the Gaussian integral that will, and this will be the inverse.
Okay, yes, of course. Okay, thank you.
Over R space.
Yes, we should. But well, I tend to omit this integration, but I will keep it for some time. Yeah, so phi is the field. It's a number, it's a Grassmann number that is defined at every point in space. Actually, it's 2n components. Each component also depends on the position in space. And what we have here is integration over all points in space, and also it's a matrix element. So we have a column with 2n elements here, and we have a row of 2n elements here, and we have some matrix in between. So it's just matrix multiplied by a column from the right and by a row from the left. It becomes a number, which still depends on the position, so it's also integrated over all positions.
Does this partition function at the beginning contains replicas as well, or?
Just as I said, it's 2n components.
Yeah, but on the last line, why is the n power for this partition function is the denominator? Yeah, so
Partition function does not contain any. I mean, it's summed up already in the action. So action depends on all components of phi, and here we integrate over all components of phi, and this is just a number. Yeah, and the very reason why we introduced these n replicas, it was such that we can write this expression, which is valid for any value of n, and then we can get rid of this z in the denominator by taking the limit n to 0. It's a trick, it's not anything. So I can, since I don't want to take the limit n to 0, this z power n is not needed. I can just remove it, minus I, but I have to write then limit n to 0. Is it still correct? Yep.
Why we could take this limit?
We wanted to get rid of the denominator. So we would like to average this Green function over disorder. Disorder enters inside the action S. Here, V of R is the disorder, it's in the exponent. And we also had here the denominator divided by Z, which contains the same action. So we have disorder in the numerator and in the denominator, and it's not easy to average. Now when I do this trick, I don't have a denominator anymore. The only place where I still have disorder is here, and then it's much easier to work.
And why this trick is valid?
Why should it not be valid?
I mean,
There are some systems where you can't use replica.
There are no such systems.
There are.
Okay.
There are systems where you should take care when you're using replica trick, and if you do it in the proper way, it still gives the correct
Okay, let's
result.
discuss.
Okay, just then a simpler question. Usually we'll just write down logarithm and then we have this mathematical trick that logarithm is actually the limit and goes to 0. Okay, and why it valid here? I mean, logarithm
It's the same trick as with the
just-
logarithm.
Okay.
So usually you say that the free energy is the logarithm of the partition
Yes,
function,
exactly,
which you want to average, but then to find the green function, you take the derivative with respect to some source term.
And
When you take the derivative of the logarithm, you have
limits.
have
Okay,
one
yes,
of these.
yes, yes. Okay, thank you. Mhm.
Yeah.
For this momentum interaction, is it an
This one
Yeah. For the first.
looks like this, minus I level.
Okay, right. But what is the function?
This is a kinetic energy. It's the spectrum of your metal. It can be a quadratic function, e squared given to m, or any other function, which defines the dispersion relation. Actually, it can be any function, but since we're dealing with metals, it means that we only need this function near the furnace surface. So it's, we linearize it after we already did it many times. Okay, so this thing here that I just applied is the replica trick. But actually I will not use this equation for the green function. I will instead do averaging for z. So z is the same integral as here, just without these two phi's in front. They are very similar, and if you know what average z is, you can also then quite easily understand what will be the same integral for the green function. So, as I said, we did this whole thing in order to average over disorder. So average green function means averaging these forward here. So this is exactly where the replica trick was needed. I can apply this averaging just to this point, sorry, because I do not have the front. And this exponent of S, it contains disorder only in this term, V of R. All other terms are fixed, and only this V of R is random. So this averaging should be called. So what we are doing now is disorder average. So the average, and it applies to exponential of just this term, minus, minus, minus is minus, right? Minus I integral of R, phi letter, V of R, phi. So this is what I should have. And as I already discussed it in the very first lecture, I believe, we are usually working with a Gaussian white noise distribution for this disorder potential. So it's an exponential of V, which should be average of a Gaussian distribution. It's quite simple. But before I do this, let me do some other thing. I will put indices here. Phi, and I will write summation. Actually, it's just a scale plot. It's a number, and then I have a column of the row, and I write the summation explicitly just to track the indices. So this average is also an exponent minus I squared minus sum over two indices A and B, integral over R divided by 4 pi mu tau, then phi dagger A, phi dagger B, phi. So, in doing this, I have used the following identity, which we already had previously, that V is Gaussian distributed with the second order correlator equal to delta function divided by 2 pi mu tau. This is how this denominator appears. So I take this exponent, I average over V, and then I get another exponent, and actually, I just realized that this identity was never used. So there is an identity. If A is a Gaussian random variable, then exponent of A average equals exponent of average A squared divided by 2. So this is a simple property of Gaussian distribution. If A is distributed as a random Gaussian variable with 0 mean and some non-zero average squared, then this is what should happen. And I just apply this identity to this integral. So I have something. This whole thing in the exponent is distributed by the Gaussian distribution, so I have to square it. Therefore, I have 4 phi fields. And then I have also 2 V variables, and then I replace the average of 2 V's by just this delta function, so I still have a single integral instead of 2 integrals, and I have this 2 pi tau, and I have also 1 pi. That's why it's 4.
I just want to ask, like, when we have phi dagger A, phi A, it's like sum of phi dagger phi squared, yes? Just.
Phi star.
No.
This was not.
I'm just asking, can we replace the sum over A, B, like by one sum squared?
Yes, you can write sum over A of this and then square. Okay, no problem. But we will not do this. And we will not do this for a very good reason. Namely, these 4 things, they are Grassmann variables. That's why I can write the same product of 4 fields as I will just take the first one and put it in the last position. Phi A, phi B star, phi B, phi A star, with a minus sign. This is the only place where I should remember the Grassmann. So they anti-commute. I take this phi A, put it in the last position, so I commute it once, twice, 3 times. That's why the whole sign is minus. And then this expression I will write as a trace of some matrix M squared. And matrix M with indices A and B is just phi A, phi B. It's just the definition of M. So I group them not like this or like this, but I group 2 fields with different indices. And then this is M with indices A, B, and this is M of B, A. So M of A, B times M of A is the trace of the square. And as a result, I have here exponent of, now it's plus, minus here, it's plus, integral over all positions, 4 pi mu tau, raise M squared. This is M. So look, we had an action, we have an exponent of the action, and the action was completely Gaussian, it was quadratic expression in the fields phi. All integrals are simple, but after we applied this order averaging, we get a term which is of the fourth order in the fields phi. So what we have now is effectively is an interacting theory. We have interaction. This interaction is not real, it's not like a Coulomb interaction. This interaction is some form to represent the averaging of a disorder. So in any particular system, nothing interacts, but when you have many systems with different disorder orientations, you average, you get some kind of interaction. Actually, it's an interaction between different replicas. You see, fields from one replica interact with fields in another replica, although we know it's just identical copies of our system. They do not know about each other. Each copy is separate. There is no any real interaction. It's just a mathematical form. What happens after we average, we have this spurious interaction between replicas. Which is very nice, because in the end we will take the limit n to 0, so there will be no replicas. Not even a single one. There will be nothing to interact with. Okay, so the next step in deriving sigma model is the Hubbard-Stratonovich transformation. Hubbard-Stratonovich. Hubbard-Stratonovich transformation, which, so we end after averaging, we have our interacting system, so now we want to make it non-interactive once again. Hubbard-Stratonovich transformation is the following thing. I will start with the same exponent I have here, this one. Look, I write equals, and then I continue here. So that exponent over there equals the following thing. I will first write it and then explain. The integral over q exponential of what? Minus pi nu over 4 tau integral over the whole space trace of q minus m divided by pi nu squared plus another integral over the whole space 4 pi nu tau trace m squared. So if you look at this exponential here, it's just exactly the same as the last term. Just copied it. And then what I did, I multiplied it with the integral over q of some other exponent, which is just a number. I can even forget that there is n here. It's an integral over q of the exponent of the trace q squared. This is just a shift of the variable, so you can, if I shift q by this amount, it will be completely independent. And this integral, just of this exponent here, over q, is a number, as I said, and the number is pi nu over 4 tau to the power minus n squared over 2. Now I should say, M, this M is a matrix. M is a matrix of, who should I ask you? What is the size of the matrix M? Size.
And
Sorry?
2
2n, right. It's the same as this field phi, it's 2n component. So this is a matrix of the size 2n, and Q is also a matrix of the size 2n over which I integrate. It's just a 2n by 2n matrix. Each matrix element is the integration variable, so I have 4n squared integrals here, which is object. And since it's trace q squared, and they're all elementary couple, it's just n squared times the same integer. It's the same notion. Now, why I did it this way, so I shifted this q variable by the matrix M, and now if you expand this square, you will see that m squared term cancels against this term. And if I just write q squared minus twice the product plus the square of this, with a minus sign, we cancel the square of m there. So nothing changed so far, and it still continues what this exponent is.
Sorry, stupid question. Q is a normal
Stupid
complex
questions not
or
allowed.
Krasnow?
Sorry?
Q is normal complex or Krasnow?
Q is real.
Q is real.
Well, actually, q is real. You see, it's minus q squared. So if it would be a number, I would say it's a real number. You integrate on the whole real axis, you have just the Poisson integral. If it's a matrix, what is the generalization of real number to matrices? It's Hermitian. I mean, Hermitian has real numbers in the diagonal, so Q is actually Hermitian. Q is Hermitian. Yep.
This insertion is on trivial case, right? So when we go from that to that, we insert a face. That is not
So what?
a face. It is not equal to one.
There is no phase.
So you say that this is a one insertion.
No. This thing equals to this. And we just multiplied the exponent with a q integral of this number, which is just a number. It's not a phase, it's a number. He's written what this number is.
Okay.
And in the replica limit of n goes to 0, this number becomes 1. So in the replica limit, we just multiply the whole thing by 1. That's why it's the identical transformation. Well, so what I wanted to do now, I just expand the square, I cancel the m squared term, and I'm left with minus pi nu over 4 tau, integral over the whole space, trace q squared. This is, if I take q squared from here, and if I take the product q times m, what I get is plus 1 over 2 tau integral over the whole space, trace q times m. That's all. And now, at this point, I recall that m is the product of two phi fields, like here. So this expression is quadratic in phi fields. And I also have other parts of the action. I took only the one with v. I also have some other parts with epsilon, psi, omega, others that are also quadratic in phi. So I can combine the part that I had in the action before with this term, and what I get is the new action that looks like this. Now it's the action that depends on q and on phi, and two things. And it looks similar to the original action. First, it has this term, which I call pi nu over 4 tau, integral space trace q squared. And then I have all the rest in. I got there minus I integral over space, phi dagger, epsilon minus psi of p, minus omega over 2 lambda, I0 lambda, and this term. And this term, which has q times m, m is phi star, so I can represent it as was IQ over 2 tau minus 5. That's all. So after this transformation, what changed? We introduced a new variable q, which is our new field. We have our old field phi and another field q. So now action depends on both. And the action is with phi, it's the same integral, the same action we had before, without random potential. There is no v here anymore. Instead of this v, we have IQ over 2 tau. And we have this first term, which depends on the q. Yeah.
Will cover storage work if we will consider Q just the real number mathematics?
But M is a matrix. M is a matrix.
Okay, no problem, but still this formula will work out.
You mean if you add a number to a matrix? Or?
Yeah.
No.
This is just the unit matrix times real number.
It will not work because if you have a unit matrix and then you add some other matrix, it's no longer diagonal, no longer trivial. This integral will not give you this thing.
Okay.
So up to this point, our whole calculation was exact. All the transformation we did are just exact transformations, exact averaging of the Gaussian distribution, exact Gaussian integral over Q, exact transformation of terms. And once we arrive at this expression, that we will do some approximations afterwards. So, are there any questions after this point? Yeah.
We can effectively consider phi as a field with multiple components that should influence somewhere like normalization coefficients. We would just say always that in the right limit, they are equal to 1.
Normalization. Well, in a sense, yes. For any observable quantity like a green function, we always have this similar denominator, so it doesn't matter how you normalize. And you're right. Since in the replica limit there is no denominator, also in the replica limit it doesn't matter how you normalize, because this normalization factor will be in the n power.
Just so to be careful, because now S is S for this multi-component field and changes. But yeah.
Well, as I said, we multiplied by something which actually normalized to some random thing, but we use the fact that n will draw to 0 in the end, so we don't care what this number actually is. And if we do not have this replica limit, then you're right, we should always include these normalization factors to make it such that all the integrals are really equal to 1.
Question.
Yeah.
So every step that we did so far, they were exact.
Yes.
So the natural question arises: why do we prefer? What advantages do have Q matrix compared to M matrix?
The advantage is that on these terms, it's easier to do the approximation that we are going to do.
And why is that?
Well, because we have a lot of experience with diagrams before. I mean,
Can argue with that.
this is exactly equivalent to the original action.
Absolutely
You can do
right.
whatever way you like, but it turns out that you cannot solve the problem exactly. You still need a small parameter, you still need some expansion. And we did this transformation because in these terms, the expansion is easier.
And what can we do with? Why can we do expansion for Q that we can't do for M?
Well, first of all, M is not very
I meant for fine.
Pfizer. And second, first we developed some understanding of how this small parameter enters and how to do approximations using diagrams. And this is just a way to represent these diagrams. So I will finish the derivation here, and then I will show the correspondence between the diagrams and the sigma model. There it will be clear why we need it exactly this way and not any other way. Well, so since this board cannot be raised up, I have to use the other one, which means I'm going to cover this thing here. So if there are no questions to this part, we will After no questions? Yeah.
Can you use this formalism to compute fluctuations of the Green's function
Yes.
also?
You can actually average not just one green function, but the product of two functions, 3, 4, any variable. You just need to add more fields here and then pre-expand. And as I already said, we will actually not use this formula because it's just a very simple case, which is not so interesting, and on that it was just to demonstrate how the replica field works. Okay, very good. So I'll continue. We have a new action, which is hidden now. With this new action, we should do some approximation to proceed further. And actually, wait, I can do one other step, which is exactly. So, oops. Go back to our new action. So, as I said, this new action is now again quadratic in the field phi. It has some other field q, which is also quadratic here, but it also has an interaction. Q interacts with phi due to this term. So what we can also do to this action, we can integrate out phi fields, because now it's Gaussian again. I mean, the action is quadratic in phi. We can take the integral, just a remain short remainder from mathematics. If you have a Gaussian integral over Raster fields, the exponent, which contains minus phi dagger a phi of any matrix A, the result is the determinant of A. And another fact from mathematics, whenever you have a determinant of A, it's the same as having an exponent of the logarithm of the determinant of A. This applies not only to determinants. And another fun fact is that whenever you have a logarithm of the determinant of a matrix, it's the same as saying trace of the logarithm of the matrix. So determinant and trace are very similar. If you take log of 1, it's the same as taking log under the second one. See, when you interchange logarithm and determinant becomes trace. So if I want to integrate over my fields phi, some quadratic expression, I will get a determinant of this matrix, this one in brackets. And then I'll do this thing and I will write it as an exponent of trace of a logarithm. So my action has this first term, nothing changed to it, and instead of this whole second thing, I will write minus trace of logarithm of this thing in square brackets. Epsilon minus psi plus omega over 2 lambda plus I0 lambda plus IQ over 2 lambda. That's it. Minus because action goes with minus in the exponent. So since it's here, I have minus. This minus and since minus. And now this new action no longer depends on phi, it depends on lambda. Yep.
We just repeat what was the I.
With what? With I, it's here. Well, actually, look, I still can drop it because when you have a logarithm of product of two things, it's the sum of two logarithms. It's log of I plus log of the rest. And then there is a trace here, and this trace involves also summation over replicas. So this log of I will be multiplied by the number of replicas. And the number of replicas in the end will be taken to 0. That's why I actually don't use it. But if you like, you can keep it there and it will not change any result in the end. Well, now one simple remark that this logarithm, this trace of very non-trivial things, because as I said, for a matrix you can easily prove this, and the object here is also a matrix, but it's a very, 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 very big matrix. What's the size of this matrix? In square brackets.
2n by 2n still? No?
Any other options? Any other opinions?
Operator. That's a product of size 2 matrix on size.
Yeah, well, I understand what you're trying to say, and it's correct. So it's an infinite matrix. It's 2n, but it's also an operator in space. So it was,
of course.
was this R integral. So each point in space, we have our field phi. It's a different variable at each point in space. And this is an operator. It's like a huge matrix which relates any point in space to any point in space. Yeah.
In our space, we, in the echelon, don't have the matrix, we have the trace of that.
You mean this one actually? You see, we have an integral of R and trace function. So if you like, you can say that.
The integral is the trace with respect to our space.
Yes.
Oh, no, okay, it does work, we just have exactly like delta R minus our prime.
Yeah. Okay, so when I say trace of log of this object, what I mean is that this is a huge operator, and you need to diagonalize it to find all the eigenvalues. Eigenvalues means that you choose a basis in which this matrix is diagonal, and then you take logarithms of all these eigenvalues and you sum all of them, and this is the trace of logarithm for the operator. Okay, so this is our new action. 1 plus 2, and it's so nice that I will just write it once again here. Now we have the action which depends only on Q, which is pi mu over 4 tau integral in space trace u squared minus trace the logarithm of the operator, which originally was in the definition of our green function, energy minus Hamiltonian. There is no random part disappeared. There is still frequency part. There is still this I0 number which distinguishes retardant from the past. And there is our Q matrix here inside. Right. And this is an action for the field Q, which is still exactly equivalent to the original thing. We didn't do any approximations up to this point. So if we can solve our problem with this action, we solve everything. The problem is that our original action in field phi was Gaussian. We introduced it like this, and this S of Q is not Gaussian. So this first part is Gaussian, it's quadratic in Q. But this logarithm of something with Q inside is a highly non-linear thing, and it's a matrix, and we have to take logarithm of a matrix, which is also crazy. That's why, to proceed further, we need some approximation. And to do an approximation, we need some small parameter. Who knows where a small parameter is?
H bar or new tau?
This one.
Yes. Still, this is the only parameter in our problem, right?
Yeah, I'm just thinking how small it actually is. I would say it's a large parameter.
Yes, for sure, but like 1 over x.
Inversely.
Yes.
Yeah. So the approximation that I'm going to do is based on the fact that the number staying here is in some sense large. Where in a metal, the density of states is large. We have large Fermi surface, the density of states is large. So this prefactor here is a big thing, and we have this Q squared, which is the dominant part, and something like that. It's probably not so big, but it's a logarithm. You have no idea what it means. So what we do first, approximation number 1 is called saddle point. Saddle point approximation. Strange name, actually. Saddle point. It means that we have an action, and you know in classical physics that anything tries to minimize its action. Whatever happens in our world happens to minimize the action. So let's minimize this action and see what happens. We want to find the value of this matrix Q for which this expression is minimal. And I would say the minimal point, but for some reason it's custom to say saddle point.
Sorry, just for the sake of clarity, this is not the general multiplication factor, this big parameter. This is, it stands only near trace Q squared,
Yes.
right?
So we want to find the minimum of this object. So how do we find the minimum? Who knows?
Differentiate.
Sure.
We take a derivative, yes, and we look where this derivative becomes 0. So we take a derivative of the action with respect to the matrix Q. But the matrix Q is the matrix, first, and second, it also is different at different points. It also depends on the point in space. So this is R. So this is a very strange type of derivative. I take a derivative in the matrix Q at some particular point only. That's why it's a variation. So I have a function on Q, variation of derivative will give me a what? A function. Yeah, that's quite easy. For the first term, it's quadratic, so it's pi mu over 2 tau Q. Now, when you take the derivative of something squared, you get twice the same thing. So it's twice, because it's the same thing. And there is no this integral over R anymore because I took a derivative at one particular point. So it's Q at that one particular point. Now, what is the derivative of trace of the logarithm? Any ideas?
Trace of 1 over everything is squared.
It's actually, yeah, the derivative of the logarithm is the inverse. So it's the inverse of this whole thing we have here in the brackets. Inverse epsilon minus psi of p plus omega over 2 lambda plus 0 lambda plus iq tau inverse times the derivative of what was inside. Inside was I over 2 tau q is it. Now, this is taken at a particular point where we take the derivative. And this thing, we should also take a derivative at the same point. And this thing in brackets, as I just explained, is a huge operator which acts in the whole space. But we take a derivative only at one point, which means that we should take this operator at the same point. It's a diagonal matrix element of this operator taken at the point R, and actually Q is taken at the same point R, because the derivative is taken with respect to Q at the same point R.
Why R? Ah, because we have
It's a diagonal.
Yes. Okay.
And this should be 0. Whenever it's 0, we have a certain point, we have the minimum of the action. So, you see that we have some equation for Q that should be solved in order to find the minimum of the action, and this is not just an algebraic equation, it has some inverse operator inside it. But this is an operator that we have seen many times, it's actually the Green function. Green function is exactly the inverse of energy minus Hamiltonian. Well, frequency just shifts the energy. The only distinction from the Green function is this strange Q that appeared here. It was not in the Green function originally. And as I said, Q depends on the position. This operator is complicated depending on the position. So let's find first some simple solution. Simple solution means let's assume that Q does not depend on the point. Q is constant. Everywhere in space, Q is the same. And it's very easy. This is a number. And here we have still an operator. It contains momentum operating inside. but it's already diagonal. It's diagonal in momentum representation, so we can simply invert it. And so I'm looking for a saddle point which is Q equals constant, does not depend on R. And for simplicity, I will also assume that omega is 0. This is actually a very nice assumption because Q equals constant means that we consider the solution with 0 momentum. This means that we consider a solution with 0 frequency. So for this particular case, what I have is pi mu over 2 tau Q. Now it's a matrix, but a number, it does not depend on R. Equals, so this should be 0, so equals pi over 2 tau, and then I have this operator. And I have to invert it, and then take a diagonal matrix element. So the inversion is just 1 over this thing, and the value at any particular point, I have it as a function of momentum, means the Fourier transform. I have to go to real space representation, so it's the integral of all momenta, d-dimensional divided by 2 pi over d, of this thing going to the denominator epsilon minus the psi of p. Omega is 0, I is 0 lambda, I q over 2 pi. And we did such integrals many times before, and we even had an equation like this before. So just to remind, because it might look not immediately familiar, this equation is nothing but self-consistent Born approximation. The equation that we had for the self-energy for the average Green function. When we included the diagrams which do not, with non-intersecting the Puget lines, was called self-consistent Born approximation, and the equation was like this. Sigma is this diagram with the Green function inside, and it's an integral over momentum of the Green function of p of the Green function, which was energy minus psi minus the same self-energy. And here was also 1 over 2 pi mu tau because we consider. So this is the self-consistent Born approximation equation, and this is the equation we have now. So you see that sigma and q is more or less the same, up to some factors. And this means that we do know already the solution. The solution is Q equals, just to remind you, sigma after we solved this equation was I over 2 tau.
I over 2, I nu over 2 tau, I suppose.
Look, sigma is I over 2 tau,
Yes.
and sigma is just here.
Yes.
Sigma is minus I. Okay. Sigma is minus I over 2 tau, it's minus up here. And
here we have additional.
we have already I over 2 tau q, so actually the solution is q equals 1. Q equals 1 for retarded function, or -1 for advanced function. Just because this invention of a shift of energy should be of a different sign. It's like this I0 lambda here, so lambda is plus minus 1. And this thing has the same sign as this one, but here we have 0, and now this 0 is replaced with 2 tau. Exactly as it was when the average between function of the disorder. Actually, this object here, 1 for retarded minus 1 for advanced, the name is called lambda. Well, okay, so it's described here. So this is the equation, and here is the solution. Q equals lambda. This is the saddle point our action. Our action is minimum when u equals lambda. Is some more for this. Well, so actually there is some, we already see that this whole story was not in vain. We know that for methods with disorder, this self-consistent word approximation is good because it's just let me finish. It's good because we have a small parameter and all these cross diagrams are small, so that we can neglect them. Then we have this approximation, then we have this 1 over tau, and we see that the action we derived is minimized at the point where this Q matrix reproduces the self-consistent word approximation. So if you like, you have a highly complicated nonlinear action, you throw it into the window and replace it with just its minimum. You say, this action is minimized, I'm at this point, I don't care. That means you just reuse the self-consistent word approximation. So if you compute the integral, if you replace this action with a number, with its minimum, all the Green functions you computed will be the same as doing self-consistent word approximation. And if you want to go beyond self-consistent word approximation, if you want to include some diagrams with crossed lines, if you want to consider localization, quantum corrections, or whatever, you should do something, you should include something more than just this single minimum classification. Yeah?
I just have a technical question how you arrived at the equation above your conclusion of the example. So how did you arrive at the integral of P?
You mean this integral?
Yes.
It's an operator taken at coincident points. Let's do it slowly. You have an operator, a matrix, which depends on 2 points, r and r prime. It's like the row index and the column index. It's an infinite matrix. Then you do Fourier transform to momentum representation. So you divide that this matrix is the integral over dp and dp prime. I'm sorry, I will need this to exponent of IPR minus IP prime R prime, and then this same matrix and momentum representation, dp prime. This is just the change of basis. Now, the matrix that we actually have depends on one momentum p, which means that this A of p prime is actually A of just a single p. It's a diagonal matrix of momentum representation, times the delta function of pi of p minus p prime. This delta means diagonal, p equals p prime. Now, since p equals p prime, I can replace this p prime with p. The integration over p prime removes the delta function. There is no p prime integration, there is no delta function. And finally, I need this matrix at coincident points when r equals r prime, the diagonal element. When r equals r prime, this exponent also goes away, and this is the momentum integral just of p.
So now this is solution independent of the dispersion, or
Independent in the limit in which we work. When we have a good metal with big Fermi surface, large Fermi tau, so this momentum integral actually is replaced by the psi integral. The only thing knows about dispersion is the density of states, this new parameter. So we approximately computed this integral approximately only in the vicinity of the Fermi surface. Okay.
When you make this Fourier transformation, can you explain why do you take plus for the first term and minus for the second term?
No, it's sorry. It is right this way for a matrix. Okay. So it's a usual Fourier transform, usual for the first index and unusual for the last one. And if you have only one index, then you have only this. This is for the column vector.
Could you show how to derive green function from Q? Because it looks like green function is variation of some file from some class of variables with action, and action now doesn't depend on class.
This is a good point, but actually I don't want to go into this, but I can tell you the words. So you need these extra files in the grip before the exponent, and instead of doing this, you can add Hamiltonian some source term, some matrix element which exists only at one point and only in one replica, and it will be just part of this, and we can continue the whole derivation up to this equation. It will be still inside. Then when I say let's consider omega equals 0, I also consider this parameter to be 0. So this is still correct, and then I do perturbation theory. I say this is my average green function. Let's recall now that we have this parameter in the denominator, take a derivative, and you will get then the green function equal to Q. Well, actually equal to what we have here. It will be here inside, you take a derivative, so it will be here inside, you take a derivative, you get the inverse of this operator, which is the green function. We just replace Q with lambda, so it's plus or minus sign 2 tau, otherwise it's just the same. Okay, so as I just said, we found the minimum of the action, Q equals lambda, and we want to do something better than just taking this minimum. So what can we do? We can find, first of all, we do an observation that this is not the only minimum of the action. There are actually many other possible values of Q, which also minimize the action. Actually, there is the whole manifold. It's so important, I should write it here. Saddle point is actually not a point, it's a manifold. Saddle manifold. You know, I'm not a mathematician, so I don't know what the manifold is. I just learned this term so many times. Saddle manifold is when you take your matrix Q, which equals lambda, and multiply it with some matrix T on the right and T dagger from the left. Turns out that if this T is just some matrix, unitary matrix, T is a unitary matrix of the size 2n, it's Q of 2n. If you do this rotation, this equation still holds. You can say this. We have lambda here, we have T and T dagger on both sides. And we can take it out of this -1, take it out from here, cancel, and the equation still holds. So when you take Q and rotate it by some unitary rotation, the equation is actually equivalent, provided that omega is 0, this term should be absent. This term is also 0, it already has 0 inside it. And this matrix T is constant in space, which means that it commutes with itself. So is the operator, which depends on momentum, it commutes with anything constant. And this object here, you can take one matrix lambda, which is just 1 minus 1, just take the lambda is 1 minus 1 single matrix. And you can rotate it, this n-dimensional unity and n-dimensional minus unity, and then you can rotate with any 2n unitary matrix, and you are still at the minimum of the action.
Sorry.
Yeah.
Why T is a constant in space? Because
Why what?
Q depends on point in space.
Yes.
Why T is independent?
Because Q is also constant.
Okay, so this
We are now
this
talking about
when Q
something which is constant in space. And at 0 frequency. It is still that approximation. So we have found one point which corresponds to some consistent form. Now we say that actually it's not a single point, it's a whole manifold, this, which can be generated like this. And actually it can be traced back to something that was erased a long time ago. Here. That's why I will not mention it.
And how could we actually found a saddle point? I mean, we now have a transformation. We fix some saddle point. Now we say that we can rotate it anyhow and get a full manifold. Yeah. So there is in this functional space there is a direction in which of Q. I mean.
It's just a metric space.
Okay, metric space.
It's a constant. It's not.
Yes. I mean, there should be some direction in which this derivative will be.
In which second derivative will be 0. We didn't compute second derivative.
We just found the minimum. Yeah. Yes, and it. Okay. Thanks.
Why can we not neglect the lambda matrix itself for approximation, because it's much less than
this one,
which is also a root number? Yeah.
This one. We can. Well, actually, I keep it here because it defines what style of the imaginary part we need, which function is retarded, and which one is advanced.
Okay, but
and this tells us that Q should be 1 for retarded and -1 for advanced. Once we know this, we can indeed just vote. So this I0 is replaced with I over 2 tau exactly as it was for the green function, for the San Francisco model.
No, it's not correct that T cannot depend on coordinate because it does not commute with psi.
We will discuss it in a minute. So we just, right now it's only the statement that whenever T does not depend on coordinate and is a unitary matrix, we are still at the minimum of the action. What happens when it does depend, I will show shortly. Yeah?
Kind of similar, but if Q in R space is diagonal constant, that means that applying any unitary transformation in R space will not change Q.
What is unitary transformation in R space? It's going, say, from R space to P space. This is a unitary transformation. I mean, in a sense, it's a constant. It does not depend on R. It's like unit operator. Any transformation you apply to a unit operator, it remains unit. That's why we don't need to do this. And in this component space, it was not unity, it was lambda, it was 1 minus 1. That's why we can rotate it. If it would be 1, 1, nothing happens, right? So the same in real space, since it's constant in the whole real space, nothing happens. You can choose any basis, you can rotate from one basis to another, it's just still the same. Okay, let's move on. As I just said, to the very nice question, we are allowed to rotate this point exactly because it's some non-trivial matrix inside, which is 1 minus 1. But this non-trivial matrix is not so much non-trivial. It has a huge unity block and a huge minus unity block. So there are some rotations, some types of this matrix T, which actually commute with lambda. If T commutes with lambda, I can pull it through and cancel out, so it does not rotate. I remain with the same Q. And there is a special subgroup of this unitary group here of matrices that commute with lambda. They're called K. So this group is called G group. Unitary matrices size to n. And inside this group G, there is a subgroup K of matrices that are also unitary and also of a size to n. That's why it's a subgroup, but that commutes with this matrix lambda. And this group K actually equals the product un times un. So these are block diagonal matrices. They have 2 blocks in the diagonal, one each unitary, one in the retarded part, one in the advanced. And of course, each block commutes with with this unity, the other one commutes with this minus unity, so this total thing commutes. So we have a group G with U over 2n of all possible matrices T. But not all of them actually rotate anything. There is a subgroup of these matrices that do not change the value of lambda. That's why we say that matrix Q belongs to a manifold. This is now where the word manifold comes. which is G divided by K. So it's any matrix T corresponds to some matrix Q, but there are different matrices T that correspond to the same matrix Q. That's why we should factor out this. It's like H symmetry, and it's U to N divided by twice U N. This is the saddle wave. It's not a group. So matrices form a group. You multiply two matrices from a group, you get another matrix from the group. This is not a group. This is a manifold. It's actually a closed space. Yeah.
Probably you can give example of that one.
Probably I will do it some later point. It's not a question actually. It's a suggestion. Let me give the lecture instead of you. Okay, so this is several manifold, and this is a crucial thing. This is something to be kept in mind for the rest of this lecture. And now, coming back to the question I already had before, what happens if this thing does depend on point in space? And also, what happens if we have a finite frequency omega which is not zero? And then the answer is, whenever you have something which depends on point in space, it means you consider the situation, so this constant means zero momentum. So you consider something like finite momentum and finite frequency. You have Q and omega, which were zero. Now we want to have non-zero Q and omega, but we already did this with diagrams. We had these diffusons and couperons that depended on Q and omega, and we always assumed both things to be small. Q8 small, omega tau small. So we will consider now how T depends on the position in space, but it depends slowly, changes very little on the scale of the mean path. And we will also include some frequency, but a small frequency, such that omega tau is much smaller than 1. And since Q is T dagger lambda T, Q squared is what? What is Q squared? It's 1. And this first part of the action, trace Q squared, we will just drop it. So now we consider only Q matrices of this form. We already restricted our model to this saddle manifold. Therefore, we don't need the first term, we need only the second one. But we will consider now Q matrix which is not constant in space. And this is the last step in the generation of the sigma model, although the main step we already did. This one was the main thing to observe. The last step is the gradient expansion. Gradient expansion. Gradient expansion just means expanding in small parameter Q8 and also in small frequency. Gradient expansion means the following. Now we will consider our matrix Q, which does depend on the position in space in R. And at every point, it still remains inside the saddle manifold, which means that it's always T dagger lambda T, but this T now depends on R. And we will put this Q matrix in our action, and we will expand it in powers of small parameter Q and omega, which is the gradient expansion. So the action is, as I said, I dropped the first term, I don't need it, minus trace of logarithm of everything I had there. So it's epsilon minus psi of P plus omega over 2 lambda. Now I need this omega, I will expand this. I0 is dropped as was requested. And instead of Q, I have this T dagger of R lambda T of R over 2 tau. Look, now this operator here is no longer diagonal. Before, when Q was constant, it depended on P, on momentum, and in momentum representation, this was a diagonal operator. Now I have part which depends on P, and the part which depends on R, and I cannot diagonalize it. They do not compute. So I have a sum of two operators that do not compute. I don't know how to make them diagonal, but this one, which depends on R, depends on R slowly. Q is smaller, which means they do not compute, but the commutator is actually small. It's not zero, but it is small. And I will use this fact to expand the logarithm powers of this commutator. So what I do, I actually multiply this whole matrix T in brackets by T dagger from the left and by the matrix T from the right. It's just a unitary rotation. Since this is trace log, it's actually a determinant of the matrix. Determinant doesn't care about unitary rotation. So this is an identical transformation. And now I take this matrices T and T dagger inside, and I have minus trace logarithm of epsilon. Nothing changes. Epsilon commutes with T. These two cancel out. Epsilon minus this last term now. Actually, it was I here. So I minus T psi T dagger. This is psi plus what? Plus omega over 2 T lambda T dagger plus I lambda over 2 tau. So these matrices T, they cancel the T here and they reappear in the other terms. And now this is the most interesting one because psi depends on P and T depends on R, and we have a product of them. So for this term only, I will write without this minus sign. I will write that it is psi plus T minus T commutator by minus. Psi T dagger plus. Yeah. Just this commutator is psi T dagger minus T dagger psi. So first term is T psi T dagger is here, and the other one with minus is here. It's just the same. And now what this commutator is? Commutator psi of P T dagger of R. Commutator. Who knows how to compute commutator? As I said, we need psi only near the Fermi surface. So actually, the result will be d psi by dp. We expanded the momentum near the Fermi surface, and then we just compute this p with t, which gives us minus I gradient of t dagger. And d psi by dp is the Fermi velocity. So this is density. Minus I, Fermi velocity, gradient of t dagger. And if I put it back here, I will have minus something. I can take advantage of an eraser. I don't need to reproduce all equations every time. So it is minus psi, this is the first one. And then the term with the commutator is minus I V Fermi plus I V Fermi T gradient T dagger. So it's T times commutator. And exactly as we discussed, t varies slowly in space, which means the gradient of t is small. Gradient of t is actually an order of q. And this term is small exactly because of this qa, small parameter. And this second term is also small because of the omega tau small parameter. So these two things, this one and this one, are two small terms inside this logarithm. And the others, epsilon, psi, and this one, are not small. That's why when we did this sigma point, saddle point calculation, we actually had only these three terms, epsilon, psi, q. Yeah? Because they are leading. Now we have two extra terms, which are small corrections. And I will.
Is next I hear a number or an operator?
This one.
Yeah.
This is an operator. Well, depends on the representation. It's a number and momentum representation and operator in real space.
We could be on this Fermi surface.
Sorry? We took what?
Velocity on the Fermi surface.
Yeah.
Or we can do the same side.
Well, you can take it on the Fermi surface, it will still be psi of p. It's psi of p everywhere, including the Fermi surface. On the Fermi surface, it's actually zero. Fermi surface is where psi turns to zero. Okay, so gradient expansion means that we now take this logarithm and expand it just in power series in these small objects. And I will call these small objects A and B. Just short. This will be A, this will be B. And I will write it once again as minus trace logarithm of this first three parts, epsilon psi, this job is actually exactly what we have in the denominator of the green function. So it's inverse of the green function. Plus A plus B. And now this green function is a matrix which contains the target and the advanced function of the diagonal. Yeah, because it's a lambda there, so it's one for one diagonal element, minus one for the other, so it's two green functions in one matrix.
We take velocity. We take the velocity and the velocity because we already have small q there, right? That's the purpose of approximation. Okay.
This is q.
Yeah, I mean.
This is velocity.
Yeah.
And we should compare this to this. This is one of tau. So if you divide one by the other, you will have tau times b is a. This will be q times a.
Yeah, I mean.
Yeah.
I will take the formula of the computation.
Which one?
The formula of the computation. C.
This one?
Yeah. No, the one above.
This one?
Yeah.
As I say, t is a small function in space. So if it is constant, zero, they commute. Oh, no, sorry, it's a different. I said that in general, this is not correct. This is correct only near the Fermi surface. Just because I know that our diagrams or momentum integrals are always, in the end, are limited to the vicinity of the Fermi surface. So if I'm close to the Fermi surface, I can just expand this function psi in powers of p near the Fermi surface. So like, it's what is written here is d psi by dp times p minus p. This function. And then this is b Fermi, this is the velocity, this is the number. And this is an operator which I can use to get this gradient. It's a lot of cheating in what I'm telling you. But the result is still correct. So, I believe I don't have much time left. That's why now we will speed up. And we expand the logarithm in powers of a and b. So there are two things. Thing number one, is actually this A thing, but omega is easy. Let's expand it in terms of A. So we have minus trace of G times A. It's the expansion of the logarithm up to the linear order in A. Which is, I should now use my green function, it's the same as I had in this STB equation up there, minus trace integral all momenta, the green function is epsilon minus the sine of p plus I lambda over 2 tau. Green function is just epsilon minus the sine plus the second inverse times the operator A. Operator A is omega over 2 T lambda T zero. And then there is a trace which acts on the whole process. So then I can do this integral, just I integrate over sine as usual. And actually it's the same integral as there, so I can just replace the value of this integral by lambda itself, because it is part of the saddle point equation. And if I do replace, what I get is, so I replace the integral with minus I pi mu lambda. Minus I pi mu lambda. I pi mu minus cancelled, omega over 2, lambda t over trace. Now, since it's trace, I can take my matrix T dagger and put it in front, in the first place, just do a side permutation, and then I will get T dagger lambda T, which accidentally is the same as Q. Therefore, I have I pi mu omega over 2 trace of lambda times Q. Since my lunch time is gone. 3 minutes. More than enough. Then there is a second part, which is the expansion of the same logarithm in the powers of b, and since I have this vector v form inside, I have to expand to the second order, and when I expand the logarithm up to the second order, 1 plus x minus x squared over 2, I have another minus. There I get trace g times b times g times b, the second order, with 1/2. So I should do the same. I should take this b, that g, like this denominator, the operator b, then another denominator, another operator b, invert this simple diagonal matrices, integrate over the whole momentum, average over the direction of the Fermi velocity on the Fermi surface, and the result I will get after doing this is the following. It's pi times mu divided by 4 times diffusion constant, v Fermi squared, tau divided by the dimension of space, trace of the gradient of the Q matrix squared. And this is your homework to do this calculation. I already gave you the answer, so you know how to do it. You know where it should end up. So these are the two things that you need for our gradient expansion, this term and this. Thank you, and yeah. T is the diffusion constant, which we introduced in our first lecture, and which is equal Fermi velocity squared times tau divided by the dimensionality of space.
And why do we need first order in A and second in B?
Because B is a vector, and when you average it, first order of vector is 0. B it has this combination on the side, so after the average, any other questions? Okay, then. Yes.